thanks to the rest of you for coming. And it's great to come out here and actually give a talk rather than be scrounging for equipment. But I do appreciate that too. I've had a lot of fun working with Chuck and Jim in the mountains in the Pacific Northwest. So I'm going to talk today about floods, and you're going to wonder what's going on here. This is I didn't get the memo that this was about the Front Range and floods in the Front Range, but you may not realize it, but right now there's a flood going on in the Grand Canyon. And this is an artificial flood generated from a release from Lake Powell and Glen Canyon Dam. And what you're looking at here are the bypass tubes releasing water down the Colorado River. And you might say, wait a minute, aren't we kind of in a dry period, and why are they doing this? Well, I'll show you. And this has a very interesting connection, actually, to the talk I'm going to, or our talk about the Front Range. Huh? Maybe it's my computer. Okay, voila. Okay, so they actually have raised the flow from, an average of about 8,000 CFS or so, cubic feet per second, to up to close to 40,000 cubic feet per second. So anybody who was rafting in the Grand Canyon right now is having a whale of a time. Now, why are they doing this again? Well, it's to replenish the sand on the beaches in the Grand Canyon, which are the only place people can camp. They're also important. The beaches and the sandbars are important for our fish habitat as well. But the goal is to try to suspend sediment that's lurking in the bottom of the river. You notice the river is pretty clear right here, but there is a lot of sand on the bed of the river, and the goal of the release is to put that sand into suspension, and it'll diffuse laterally onto wherever there's surfaces like this and build sandbars. So these are called beach-building flows. Now, the source of the sediment is a river right downstream of Glen Canyon Dam called the Paria River. And it's the only really major source of sediment for the Colorado River in Grand Canyon. And the river, because of Glen Canyon Dam, all the sediment flow down the river has been stopped by Glen Canyon Dam. And so over time, these beaches are being eroded slowly, and whatever sediment is in the river is steadily getting pushed into Lake Mead. And so the Paria River is the primary source of sediment at this point in time. So why are they doing this now? Well, there was a series of monsoon storms that hit the Paria River in late summer. And again, that, because the Paria River is a major tributary to the Colorado River, brought in a lot of sediment. And this triggers a kind of a decision-making tree where they decide, okay, we're going to release water from the dam because we've got a lot of sediment from the Paria River has piled up in the bed of the Colorado River. So the goal then is to move some of this downstream and hopefully not move it completely out of the system into Lake Mead. Now, you may notice this spike here. This is the biggest one of them. When did it occur? September 12th or 11th and 12th, 2013. This is actually the same storm that came into Colorado, or the beginnings of the same storm that came into Colorado. So I guess when I talk about the regional hydrology, I can go as far south as the Arizona-Utah border and talk about this. I'll actually come back to this because this is a bit of a discussion about the meteorology of the flood we have. So my perspective on this is based on a number of years I've been studying. I'm mostly a geomorphologist, and I study sediment transport in rivers. But to do that, I had to learn something about floods, and I wanted to study the geomorphic effects of floods. So I started learning a lot about hydrology. Then I had the good fortune of coming here to Boulder and joining the geography department, where this person, Gilbert White, was a distinguished professor. He died a few years ago, but what Gilbert White is known for is he's called the father of modern floodplain management. He's the person that originated the idea that the best way to mitigate or reduce flood risk is to get people out of the floodplain rather than try to build structural controls like levees or dams that would otherwise prevent over flooding in flood-prone areas. So he was advocating non-structural controls for flood mitigation way back in the 40s and 50s. And that idea has caught on, depending where you are, in some places more than others. But he was, as I say, a distinguished professor in the University of Colorado. And directly or indirectly, he had a lot to do with probably the steps that have been taken in Boulder to mitigate against these kinds of events. Some of you who've lived in Boulder a long time have seen evidence of this over the years, where they've taken buildings taken them out of the floodplain, and put instead where the soccer field is next to Boulder High School. It used to be a relatively large apartment complex, and things like that. All the pedestrian bridges across the stream have been engineered now and rebuilt so that they can break away in the event of a large flood. And all the major north-south roads through Boulder have been, the bridges have been enlarged to increase their capacity. So Gilbert was, I think, he's a quiet man, or was a quiet man, so he probably wasn't down at City Hall knocking on doors every day, but directly or indirectly, he had a lot to do with and this, again, I think turns out to be pretty important in what happened during our flood. So this is the Gilbert White Memorial. That's the Broadway Bridge in the background. And this was an art project that Gilbert White's daughter, Mary, initiated and got the funding for and got the okay to put down here. Now, this is taken the morning after the peak discharge. Peak discharge was about midnight on the very beginning of September 13th. And the base here, the water is just kind of lapping around the base of this monument. This denotes the 50-year flood, and the next one up will be the 100-year flood, and then the next one up is the Big Thompson flood, which is sort of the benchmark in floods around here, which occurred in 1976. If that were to come down Boulder Canyon, it would perhaps reach that level here. Now, so here we are about 6 hours, no, not 6 hours, 12 hours after the peak. And the flow is, like I say, still lapping around the base of this. And looking around, I personally didn't see any evidence that the flood got that high at all. And it was probably not, from what I could see looking around, I'm not sure it ever got even close. So this is a bit of an indication possibly of where did this flood fit in terms of return periods. We'll get back to that in a minute. Now, just a brief history. Again, I'm a geomorphologist, but I moved to Colorado to go to graduate school at Colorado State in 1982 in the fall, this time of year. And in the summer of 1982, there had been this dam failure up in Rocky Mountain Park, the failure of the Long Lake Dam. And it generated a fairly good-sized flood for this stream. It's not a natural flood due to a dam failure, but it proved to be a perfect thesis opportunity for me. I had just arrived in town, so I took advantage of this for the next 5 years and made this my field area. And so, but anyway, this is Horseshoe Park, a valley that's showing areas that were inundated by the flood. It did not do a lot of damage to this stream. It's a nice little meandering stream. But then the flood kept going down Fall River and eventually went through Estes Park and did a fair bit of damage. So now, poor people in Estes Park, they were cut off kind of from civilization by the Big Thompson flood. Then along comes this flood and whacks the town again. And now they've been cut off, well, not anymore cut off, but they were cut off for a while again, or at least somewhat isolated by this most recent flood. So they've had as much bad luck as any community probably needs for the next century. And people that control floods ought to leave them alone for a while. So this is how I got into it, flood geomorphology. So I want to give you a little background about Colorado's hydrology. This is pretty straightforward, but showing you a picture of an alpine basin to kind of reinforce or stress the point that snow is very important for us as a water supply in Colorado. It's the primary source of water. And we guess, roughly speaking, that snow melt will produce maybe 80% of our water supply. Now, the thing about snowmelt that's kind of interesting is it's driven by radiation and sensible heat input. So it's think about where the energy to melt snow comes from. It's sensible heat in the atmosphere or solar radiation, and that has a diurnal cycle. So every night this shuts down, and the end result of that is you can only melt snow for maybe 8 to 12 hours a day, and that has a limiting effect on the rate that you can produce snow melt. And one of our former grad students, Don Klein, who works for the National Weather Service now, he measured maximum snowmelt rates up on Niwot Ridge one spring and concluded that the maximum snowmelt rates are about equal to average rainfall rates, which would be something on the order of maybe 2 inches a day, something like that. So snowmelt is critical for providing water, but it's not important for providing big floods. So the floods that are produced by snowmelt, they come like clockwork. You can set your clock at May 25th, all the rivers in Colorado will peak. But they're never really big peaks, really big. So it's the rainfall-generated flows that are more concerning. So the rainfall-generated floods generally occur in the summer due to thunderstorms. The most notable example, again, is the Big Thompson flood. This is the mouth of Big Thompson Canyon here. That was completely wiped out by the 1976 flood. But there's been other ones. And go back in history, there was a relatively big flood that came through Denver. It was centered over the Palmer Divide between Denver and Colorado Springs. And again, it was an intense thunderstorm, actually in the middle of June. And again, it hit all the tributaries of the South Platte in that area, like another one further south. Anyway, so all the major tributaries, or little tributaries that come into the South Platte River in the vicinity of Denver flooded, and that they subsequently built these major reservoirs around Denver, like Cherry Creek Reservoir and Season, the other one you drive along on 470. So those have been built as flood control structures since this flood of 65. So these floods are the most dangerous by far. That would be usable in the sense of a water resource, but they do produce the biggest floods. The Fort Collins flood is another example. Oh, and it was after this that we saw that all these little signs go up and down the canyons, warning us to skedaddle up the hill in case we have trouble. So here's a year not too far in the past that illustrates the difference between these snowmelt flows and a thunderstorm flow. So this is a hydrograph going from the early part of May to the end of the water year in September. And the part right here, this is the bulk of the hydrograph, is the snowmelt portion. And then this peak that you see that occurs in mid-July or so is a thunderstorm that was centered again over the foothills a little bit west of Boulder, and that produced the largest peak of the year. But again, the volume there is not that important. So again, the difference here in terms of peaks is relatively significant. And it's these floods, this is still puny by 2013 standards, but again, for that day, it was kind of probably fun to be down at the creek. So to put this a little bit again in historical perspective, there's been a gauge operated in Netherlands on Middle Boulder Creek for a long time, and I'm only showing you half the record or so here. It goes back to the early 1900s, the gauge record. And what you're seeing here is a plot of annual peak discharge over time. This is the highest instantaneous flow of the year, and only one per year. There's another way to do this, but that's how we'll do this. And so, again, I'm showing you 50-plus years of record, or maybe 60 years of record. And the dotted line across the middle there indicates this average peak discharge. And here it's 13 cubic meters per second, which would be about 400 cubic feet per second if you're a raptor. And if you do the analysis of flood frequency, and I'll show you some more of this later on, which is kind of like some of you must be seismologists and you do earthquake frequencies, right? Where you sort of just look at the distribution of earthquakes, small and large. You fit some function to them, and then you use that to extrapolate to say what's the 1 in 1,000 probability earthquake. We do the same thing with floods. So the result of that is you can calculate a 100-year flood given this distribution of flows. And for this particular creek, it's 25 cubic meters per second, which turns out to be about 2 times the average for this. And I'll tell you this now. This is pretty typical of streams that are fed by snowmelt high in the mountains. By the way, if any of you want to stop me and ask questions, please do, because this is not that setting that you can't ask. So if you want to ask questions, please do. So that you can think about this. The variability here is not that great. It might look that great, but wait till I show you the next slide. And the result is in these snowmelt floods, the 100-year flood is barely more than twice the mean annual flood. So we're talking about a narrow standard deviation. So this is a creek now, Bear Creek, which is down by Morrison. The gauge is in Morrison, near Red Rock. It has its headwaters around Evergreen. It does not go all the way up to the Continental Divide then, in the same sense as Middle Boulder Creek. And again, I'm showing you only about half the record. This is a great gauge. I hope they never take it out because it has records that go back in the late 1800s. And again, periodically there are these relatively noticeable spikes. Some of those are rainstorms. Some of them, a lot of these are probably snowmelt. But again, this is lower in elevation, so it's not a whole lot of snowmelt. In this case, probably half the floods are generated by rainfall in the summer. The other half probably snowmelt. But here, again, the mean annual flood is marked here, a little higher than the other ones. But when you calculate the 100-year flood here, it's way off the graph, what it would be, and it's 10 times the mean annual flood. So this gets back to the point that rainfall can deliver water much more quickly than snowmelt can. And so our biggest problem with the threat for flood is from rainfall, and typically late summer. So I'll come back to this point later. So let's talk a little bit about the rain that so I'll now move to the 2013 flood and the rain the precipitation we received there. This is just the kind of, this is not from 2013. This is older, grainy black and white, a pretty image about rainfall in the front range. So there's been some discussion about where did this rain come from. I'll explain why these women are here in a minute. One explanation you will hear about this is that there was a low pressure system centered here over Utah, or basically the west of the Four Corners there. And so the typical circulation around these is counterclockwise. And this circulation system was drawing air up from the Gulf of California and Pacific Ocean and into Colorado. And I put Lucy and Ethel up here as a reminder that this is the WCB here stands for Warm Conveyor Belt. And that's why Lucy and Ethel are trying to pick the chocolates as fast as they can off the conveyor belt. And in the background, the little sign says, danger. Be careful when the conveyor is moving. And so our meteorologists could take a little lesson home about this, that when this conveyor belt is moving, we need to be careful. Now, it turns out that this isn't the whole story I got. And again, I'm not a meteorologist, so I'm just telling you what I've learned scouring the web. There's a lot of meteorologists that are big into blogosphere, so if you want to find more about this, it's not hard. So I have, this is an animation. I hope I can stop it without really stopping. And let me tell you what you're going to see. This is going to show rainfall. It's radar, and it's over a period from the 9th to maybe the 13th. So about 3 or 4 days worth of rainfall. You're going to see a lot of flow from southwest to northeast, which is exactly typical of the monsoon. Then it's going to stop, and then you'll see something different. And I think this is kind of pretty interesting, at least in terms of, and maybe I'll just let it run, and if we want to look at it again. So this is what I'm talking about, northwest or southwest northeast flow. Starting about now, you get a change, though. And you'll see stuff start to come from the southeast. And the date now is 9/12, so this is Greenwich time, but this is the time of the most extreme rainfall. Okay, and so maybe I don't need to run it again, but you can see that some of southeast parts of Denver got hammered. Now, I don't know if anybody lives down there or is familiar, but you haven't heard much about this pocket of intense rainfall at all. But you have heard a lot about this. We were right in the bullseye, the city at least, as well as this area. Estes Park is up here. But there's an area between Boulder and Estes Park that got pretty well doused as well. So the initial thing that sort of set up the moist conditions in Boulder was indeed monsoon flow. But what really delivered the most intense rainfall, and I got this from looking at somebody's blog, was actually upslope moisture coming from the Gulf of Mexico, which is typical of what we would get in spring, with our wet, heavy snowfalls, where you're bringing moisture up from there and pushing it into the front range. So that's the explanation given by one meteorologist, a forecast, maybe a retired forecaster. So, the reason this was set up, there's a high-pressure system, where would Oklahoma be? Down here, high-pressure system circulating the moisture that way, but also probably still some of the monsoonal flow, and convergence kind of right in the area, the southern Front Range and north. So, whatever the mechanism, the rainfall totals were outstanding. So these are 24-hour totals or so. And Boulder right here, this is the Justice Center, which I hope that I don't get too much personal acquaintance with, because it means I'm either in trouble or I'm evaluating somebody who's in trouble. But it's got actually fairly high rain. Shanahan Ridge is down here. Anybody if you live there, Shanahan Ridge got fairly well dosed. This might be Lee Hill Road up here, or maybe here. I can't tell given my eyes. But at any rate, Lee Hill got kind of the highest total of all. So if you've lived up in the hills there, you were in the middle. And then, again, all the way up through northern Boulder County and into Larimore County, plenty of places that got 9-10 inches of rainfall in 24 hours during the peak of the storm. And by the way, Boulder's average rainfall for a year is about 18 inches. So if you get half your annual rainfall in 24 hours, I don't care where you live, stuff's going to happen. So, it doesn't matter whether it's Colorado or Maine or Mexico or wherever. You get half your annual rainfall happen. So stuff did happen. Now, one thing that's interesting about this, you notice
because the channels are all undersized.
That's just a lot of water to put on the ground in a short amount of time. Whether they are undersized, I don't know. It's just you can't avoid, I think, a deluge or flooding with that kind of rainfall. So one of the things that I find interesting about this is as you go west, all these gauges are operated by urban drainage and flood control districts. This is a warning network system called the alert system that the UDFCD operates, and this all was put in after the big Thompson flood for precisely this purpose, to warn people and alert people that, so they have these, they're just pressure transducers in creeks and rain gauges, and they're programmed to sound alarms when the rainfall rate is reaching some threshold that they've set. And it worked brilliantly, I think. And if you bicycled up these canyons, you might have seen some of the little antennas that are next to creeks. because if you're like me, you bicycle up really slow. So anyway, so these are all recording and reporting precipitation through this whole event. It's an incredible database. You'll notice though that they don't have any really to speak of up in the mountains, because that's again where the threat of rainfall for whatever reason kind of diminishes. And this is unknown kind of meteorologically, at least as far as I know. But so what's peculiar about this is this really was upslope rainfall. I would expect higher rainfall intensities or totals up here in the mountains because of the movement and orographic uplift associated with upslope flow. But it really peters out as you get up. The rainfall peters out as you get up into above the peak-to-peak highway. And again, the storm intensity was just not penetrating that far into the mountains. And somehow but it was certainly dumping copious amounts of rain along the Front Range. So again, this is kind of an oddity about the precipitation that I've never understood. It's been recognized before, but I don't quite understand it. So for the week, the Boulder rain gauge, which is found by NIST, what would it be? They recorded over 17 inches of rain for the week, and again, that's almost a year's worth of rainfall in 1 week. So the local benchmark for extreme flooding is the Big Thompson flood, and so these are pictures from 1976 when the canyon was wiped out. And again, this was a thunderstorm. They got fairly intense rain over a period of just a few hours, and also, in addition to just the damage, about 140 lives were lost. So they did record rainfall. This is some radar estimates of rainfall intensity or cumulative rainfall on the y-axis, and then time on the x-axis here. This is based on radar data, but somewhat calibrated with, there was one precipitation station in this region. Glen Comfort is in the Big Thompson Canyon. Glen Haven is kind of just a little north of Estes Park in the headwaters of the North Fork of the Big Thompson. So I picked some limits on rain to determine rainfall intensity for this particular storm. So in this one here, at this location, they got about an average of 8 inches an hour, but only for about an hour or two. But that's a lot of rain for that kind of event. And then if I took this one as kind of a lower limit, then they got an average of about 3 inches per hour. And so this would be kind of the window, I guess, or range of values that probably fell within this region to generate the Big Thompson flood. Now, fortunately, because of the data that was available from the rain gauge network in the foothills, we can make the same kinds of comparisons. So these are data from a bunch of different places, and as I say, I could have had 20 on here. I just took about 10 that span the geographic range going from, this is the Justice Center, this is B-Rock, is Button Rock Reservoir, which is west of Lyons, the town of Lyons, Lee Hill, so on and so forth. So this kind of go from north to south across Boulder County. So I can make the same comparison here. I'm going to draw a line through, this is the most intense part of the storm, and then I'm going to draw a line through this one, and we can compare. So now you're 1 inch per hour. That's the most intense rainfall here. Remember the Big Thompson one, the two curves, one was 8 inches per hour and the other was 3. So even at the most intensity in our storm, it was still way below Big Thompson intensity. And then if you go to the sort of second phase of the storm here that lasted through the day and the next day, then it's 0.2 of an inch per hour. So the rainfall intensities from this storm don't appear to be anything like the Big Thompson flood. What made it unique, though, is this went on for days. So the Big Thompson event, really, the rainfall was over in about 4 hours or so, 6 hours, in terms of the real high intensity. But this kind of went on and on and on. Plus, it was widespread. The big Thompson storm was a really small pocket in comparison to this. So the intensities were not so great here, but they were really widespread. So let's talk a little bit about floods now. So here is the Ebenfine Park looking downstream. Whoops. There. You get the point. So, periodically you will see people kayaking this in the spring, but I didn't see anybody out there on this particular day. So again, this is huh? There were people out there? Oh. Don't tell them that, the boss is here. Uh-huh. Well, there are thrill seekers everywhere. Okay, so I'll run you through a series of hydrographs here, plotting discharge over time, starting upstream at Nederland, where there's a gauge, again, a very good gauge that's been in operation since almost the turn of the other century, almost 100 years. And so the peak discharge here is a little over 400 cubic feet per second. Remember I said that the average flood here was, maybe I said 12 mean annual, which is about 400, I think, cubic feet per second. So this is actually about equal to your average snowmelt flood. And when you take all the floods at this location, this one ranks as only the 36th highest. In other words, there are 35 peaks that are higher than this one. So for whatever reason, again, the rainfall and flooding really petered out as you got up above elevation of about 7,500 feet. Now, as you work down the canyon, there's a gauge at, it's just a location. There's nothing here. It's called Oradell. It's right before you go through the little tunnel on your way up Boulder Canyon. The gauge is just downstream of that. And there's a power plant that is also around the corner, and I'm sure that's why the gauge is there, is because they want to see whether the Excel's predecessor was using too much water or not. Anyway, so this is the gauge at Oradell. Now this turns out then to be a peak of 1,500 CFS, quite a bit bigger. So the flood has tripled in size by the time it's gotten to Oradell. So now you're 2/3 of the way down the canyon, so it's really picking up. But I've been to this site since, and it doesn't look like any rocks on the bed of the stream moved at all. The rocks are coated with algae. So that even though this is perhaps, I'll tell you, it's the third biggest flood of record in this case. So that's a pretty good sized flood, and yet it still did not mobilize much of the riverbed material at this location, because you can see that just by looking at all the algae-covered rocks. And there's very few that, maybe I shouldn't say it didn't move anything, but it didn't move much. Now, downstream of Oradell is where 4 Mile Creek joins. So that's where the discharge has really got a boost. So we're at about 1,700 CFS here, and I don't know, maybe Sheila, she might have had a number for you because she works up there a lot, and it might be about 2,000 CFS came out of 4 Mile Creek. So about doubling the flow of Boulder Creek at that point. So you come into Boulder. Now this is not discharge, this is gauge height. This is the pattern of the flow. The state operates this gauge, but and so I got but the state was not reporting the discharge. They were just reporting gauge height. And the discharge I got off the Urban Drainage and Flood Control District website. And the peak here is about 5,000 cubic feet per second. So between Oradell and the city of Boulder. Now this gauge is right upstream of the Broadway Bridge. It's you have to really know what you're looking for to see it, and that's on purpose given all the drunks that hang out down there. So we don't know where this gauge has not been operated very long, so we don't know where it would stand in kind of a historical sense. certainly not as big as the flood of record, which is 11,400 cubic feet per second in 1894. So we're not even half the flood of record at that location. Moving downstream a little more, and again, possibly Sheila mentioned this too, because this is a USGS gauge at 75th Street, and they were actually able to get out and measure. Those two stars indicate flow measurements. They actually measured the flow. And so this number is pretty good based on there were actual measurements there. Again, about 5,000 CFS. Now, what's odd about this is South Boulder Creek joins Boulder Creek above this. And South Boulder Creek should have contributed at least about 1,000 CFS. But this discharge is the same as downtown. So Sheila and I have had a bit of a discussion about where was water going, because it doesn't seem to... Huh? Your basement. Well, that's maybe not such a bad... think about it. I mean, how many houses got acted as storage reservoirs? Sorry about that, Jim, but you did the community a big service. Yeah. Not much. It did spread out a lot. So one of the things, Becky, my wife, and I were out there near there where we shouldn't have been, but this is the only way you get information these days. There are a lot of abandoned gravel pits between the confluence with South Boulder Creek and this gauge. They're ponds. One of them is near the sewage treatment plant. There's a series of ponds. Saw Hill, something like that. No, but there's a whole bunch more back where you can't kind of get to. You can see them on air photos. And I know for a fact one of them got breached, and I wonder if water wasn't going into these ponds and acting as much better store than your basement possibly. And so if you integrate the area under this curve, over time, will you get the drainage then from those ponds or when the flood water is drained from the ponds, and will that add up to the same amount of water as South Boulder Creek plus Boulder Creek? I don't know. And like I said, they don't let you in there legally. I have a question. Yeah. How did they measure flow rate? So, well, they mostly they're going out with a propeller current meter, like an anemometer that you see on top of buildings measuring wind. And they've been using the same device since they started doing this. So that just measures the local velocity in the stream. Velocity times depth gives you a unit discharge, and then times the width gives you, and you do that across the tank. So they typically, though, do it from either a bridge, but 100 years ago, when there may not have been bridges, they did it from a cable across the river. And maybe you've seen some of these on river trips and stuff. So this one here, there's a bridge across the stream. But in a lot of places, there would just be this cableway, and they go across in a little cart. It's just big enough for two people. And it's quite fun to do during a large flood. So they've been using essentially the same techniques for a long time. They now use acoustic Doppler velocimeters to get these measurements. So that's how they get these. Now, most of this, what you see, is actually a measurement of water level that's recorded either through a pressure transducer, or in the old days, there used to be a water well with a float in it that was attached to a strip chart that would record the changes in flow depth then. And so then they would build a correlation between the water level and the measurements here. And so you'd have maybe one measurement a month on a stream, and you build a correlation between the measured discharge and the measured, they call it gauge height or stage. And so the stage is measured continuously, now with pressure transducers, in the past with a float attached to a strip chart. So that's how they're getting the discharges here. Now, if a riverbed starts to scour, then the water level could go down, even though the discharge is going up. So this is where problems occur in floods. Is if the bed is filling or scouring, then it artificially changes the gauge height. And this could be a problem with, I don't think it's a problem with these measurements because I've been there and it doesn't look like that happened. But that's something to keep in mind with these techniques. So what they can do, to make a longer story longer, they can go out after a flood and make measurements and indirectly calculate the discharge using sort of standard engineering procedures. And they've done that. USGS has done that at a lot of these gauges. Okay, so the Boulder Camera came up with this headline, right, when is it? The Friday the 13th. So this is based on a call to the USGS Associate Director of the Colorado Water Science Center. And I'm not sure he was, this number came into his head, and that's what came out, and then that's what the Daily Camera reported. So this got a lot of press, as well as Weather Service media releases that said that rainfall exceeded the 1 in 1,000 year exceedance probabilities at a number of their gauges. So the rainfall, the 1,000-year rainfall caught fire real quick. And people made the association that the 1,000-year rainfall meant you got a 1,000-year flood. So that spread like, and people kind of started, so that you can't make that association necessarily. There's probably an earthquake analogy in here somewhere as well. But the reason is you could have a 10-year rainfall, but it could produce. But if it occurred over an urban area where you have no impervious surfaces, you could get let's say a 20-year event. So they don't correlate depending on whether what your conditions are generating runoff. Nonetheless, this became sort of a thing for people to talk about, and for people like me to think about. I'm going to show you some flood frequency curves now, which again are like your earthquake probability distribution. And maybe I'll just focus on these for right now. This is work that Bob Jarrett did. He's a hydrologist with the USGS that has done excellent work over the years looking at floods along the Front Range. And what he did there was split, again, going back to the meteorological conditions or hydrologic conditions that generate floods. He split flood frequency curves into snowmelt versus rainfall or some blend of the two, which a lot of our streams are. So he's plotting then peak discharge here. This is for the mouth of the Big Thompson Canyon, and then exceedance probability here. And so the mean should be, exceedance probability of 0.5. That's a 2-year flood event. And then 0.01 exceedance probability is a 100-year event, and so on. So he was the first to kind of separate flood-generating mechanisms in terms of this kind of analysis. So for when I was a little boy and doing my PhD, I did something similar, except I was working in 5 different regions across the western U.S., 2 of them here in Colorado. And so these are normalized flood frequency curves. By that, I mean you can take a flood record and normalize the individual values by the mean, okay? And then you can group data from a bunch of sites. And I don't know if do people do this with earthquakes at all? You have, faults within a system. Can you group the data, or is that a no-no? Well, anyway, we do this. We do this in flood hydrology because it's a way to deal with some of the scatter. Okay, is to pool data from other sites so you can increase your sample size and therefore reduce your uncertainty. So what this means is Q sub m is the mean annual flood. Q would be any other flood. And so a value of 1 would indicate the mean annual flood. And in these curves then, you can see they have different slopes and different curvatures. And it's all related to how they get rainfall. So this flattest curve here is for alpine streams in Colorado. This would be like Middle Boulder Creek at Netherland is one of those streams. Other ones scattered up and down the Front Range. The very steep curve here is for what I'm calling the Colorado foothills. These are streams that don't go all the way up into up to the Continental Divide, like the one I showed you, Bear Creek. But there's others. Coal Creek, south of Boulder here is one. One fork of the Big Thompson River, the North Fork, is another one. The Little Thompson River is one. So there's about half a dozen gauges that I could use to form this curve. The take-home message here, though, the important point is, if we go to a 100-year flood for streams that are where the floods are produced predominantly by snowmelt, the 100-year flood is 2 times or so or less than the mean. That's like the data I showed you before. If we go to the foothill streams, the 100-year flood is like 10 times the mean annual flood, and that's like the Bear Creek example I gave you before. So those can be kind of considered end members for flood hydrology in Colorado. So if we then go to this gauge at 75th Street on Boulder Creek, it has 26 years of record. It's in operation now, so the record started, 27 years ago or so. But I can tell from looking at this, now again, I'm normalizing the data by the mean here. So 1 here is, it's approximately the mean 2.0 is the mean. It has a return or exceeds probability of 0.5. So that should correspond roughly to the mean. So this looks like a nice distribution. This is probability paper here. This is a log scale here. So probability paper, again, you might be familiar, it's not log paper. It's stretched in 2 directions away from the middle. Okay? And so this is a probability of 0.01, 0.5, down here 0.99. Those are the probabilities. So this looks like a nice flood frequency curve to me. But we'll put the 2013 event on, and it sits there. And so it's really an outlier in comparison to the measurements that have been made so far. So this is a really common problem in flood frequency analysis. And so the question is, what do you do with this? And you could say, well, I'm going to ignore it and just call it an outlier. But then that's kind of sidestepping the issue. You could say, well, okay, I'm going to extend this curve here, and I'm going to move the 2013 flood out till I intersect that curve, or that line. Well, then you'd have a 1,000-year event, or maybe even 5,000-year event. Now, does that make sense? So, we don't know. So you're so the solution to this, like I say, is regionalizing data and pooling data together. So I'll show. This is data from these streams: Bear Creek, Turkey Creek, Left-Hand Creek. Left hand's another one of these. Doesn't go all the way up to the Continental Divide. Coal Creek, North Fork of Big Thompson, Little Thompson. What's that? 6 streams, probably total of about 300 years worth of record, overlapping in many cases, but not in other cases. And then each data point or each flood normalized by its mean, and you can see that you could probably just eyeball yourself a curve through there to get what would be I will call a regional flood frequency curve. Okay, and so we can do that. That's the curve. And one interesting thing is it turns out that, again, this is a log scale. Even when you take the logarithms of floods, these distributions are very skewed. They're not normal anyway. And the result of that is the mean here is actually about a 5-year flood. I don't know what it looks like from your vantage, but so the average on these rainfall dominated streams is more like has a lower probability of occurring than just 50%. Okay? So now what we can do, though, is take this curve, go back to the 75th Street gauge, and plot this curve on that relation. So here you go. Here's the 2013 flood. And if I plot my regional curve through it, it looks like this. Now, it doesn't match the observations well at all, but that's, to me, not surprising because many of these floods are not generated by rainfall at all. They're all snowmelt floods, even in Boulder. Plus, we have regulation by Barker Dam, as well as what's the one on Gross Reservoir on South Boulder Creek. So there's a lot of regulation here, but essentially very little regulation of that flow. And the curve goes through here, and then you can bring, this is the 50-year flood, that's the 25-year flood. So my estimate on this is this flood of 13 at that location was somewhere between the 25 and the 50-year flood, not a 100-year flood. We can go downstream to, there's another gauge at the mouth near Longmont, do the same thing. Oops, they made measurements here. This goes out to just yesterday or so. So this is a much longer record. Here's where I'm confused. Discharge there is much higher than the one at 75th. Here's the flood frequency curve with 2013 plotted. Now this flow here is a rainstorm in September in 1936. So it's not like these events have not happened before. It's not as big as the one we had just now, but it's approaching that. So if I put my regional curve through here, now this one is, that's the 50-year flood. That's the 100-year flood. So this one, at this gauge then, it probably exceeds the 50-year flood, but it's not a 100-year flood. So this one is indeed starting to get into the extraordinary category based on even my regional analysis. So one take-home message from this is we don't have to think that it could have been a 100-year, maybe in Lyons, that's what happened. It really was indeed a 100-year flood, no matter how you crunch the numbers. It does not appear that way in downtown Boulder. The last thing I'll show you then is the city of Boulder has done a lot to sort of prepare for events like this, and they've got excellent maps delineating areas that would be inundated by floods with different return periods. So this is sort of, you know, Boulder proper, and this is South Boulder Creek here, and these are the little tributaries. And this is what they expect would be inundated by a 25-year flood. This is based on modeling of given a discharge of a 25-year flood. And if any of you were walking around downtown, this is Boulder Creek right here. This is the core of the downtown area here. You don't see a whole lot of water out of banks at this flow. And if you were walking downtown during the flood, you would not see a lot of water out of the banks. There were places where it was. Yeah, is your basement over here, Jim? So sorry for those of you participating outside. I think I can do it. Almost done anyway. So let me fast forward to the next. You can see South Boulder Creek was actually a real problem, and there's places here where it gets hung up against some of the cross streets and things like that. And that was potentially a problem. So if we then go to the 50-year flood, things start to look a little more serious, and then we do start to see some flooding in areas that would be were not flooded downtown. And then if we go to the 100-year flood, did that switch? Looks like the same to me, but maybe I'm getting colorblind. If we went to the 100-year flood, we would see plenty of water flooding streets in the the highly populated areas within Boulder, as well as all along South Boulder Creek and then further downstream. So that level of inundation does not appear to, it doesn't appear that's what we were seeing. Now you could say, well, these maps are wrong. Well, if that's the case, then they're going to have to redo them. So this 100-year flood designation is really important from the standpoint of insurance. Because if any of you live in certain areas, and they change this floodplain next time they change it. So that leads to a lot of meetings at City Hall and so forth. Okay, so if I can just summarize then, I wrap this up. As I said, the rainfall was probably most exceptional in terms of its extent and its duration, but not its intensity. It's interesting how the rainfall did not get way up into the mountains and it was concentrated sort of in the canyons, just like, and again, this is what Bob Jarrett of the USGS kind of warned people about a long time ago. I think the mitigation that occurred in the city was critical to why damage in the city of Boulder was not anywhere like it was in Lyons or even Longmont. Longmont has gone to great lengths to mitigate for events like this, but the St. Vrain had a mind of its own and just completely jumped its banks. And even though they finished the mitigation along the St. Vrain in Longmont, the creek said, well, I don't have to worry about that, and completely. So, you know, you can mitigate, but if the creek, something weird happens and the creek makes a random move, then the mitigation is not useful. So it's really kind of odd that Boulder got very lucky in some senses then, I guess. I would say that, again, the inundation maps that have been prepared for 25 years flood look consistent with what I saw, you know, riding my bike through town and walking through town. So at least along Boulder Creek and Boulder, I don't know that it was I think it was significantly less than a 100-year flood. And then, and I'd say, like, that doesn't mean it was a 25-year flood everywhere. And certainly in Lyons and places like that, and then maybe in Longmont too. St. Vrain might have been much more intense. The last thing I'll leave you with, if you're looking at where this rainfall sits worldwide, this is a map that's kind of, or a graph that's kind of cool. It shows duration of rainfall going from a few minutes on up to 2 years, and then over here is rainfall, and this is the worldwide maximum. And this is a place I want to go to in India sometime because I want to see what 10,000 millimeters, that's 10 meters of rainfall in a year look like. But at any rate, for 24 hours, the record is somewhere in the neighborhood of 100 inches, and Boulder is down here at 9. So we're a long ways away from anything that would be considered a world record. It probably wouldn't be too bad for Colorado, though, because if we were to draw a curve for Colorado, it would probably sit lower, but we could do that. So it was exceptional, but pretty much local. So I'll stop there, and I'll entertain any questions you have, and or we can talk about it later off the line. So thanks very much.
So in Lyons, we lost power at about noon on Thursday. But the last thing I heard on TV was, when I was watching the news, is that there was a 25-foot wall of water coming down Boulder Canyon. Was that reality, or did the mitigation efforts and the along the Boulder Creek?
So I've heard the same story about the 25-foot wall of water, but I don't know that it happened. I could go back to one of the slides where the gauge downtown, I guess I showed it, there is a huge spike in that. But I think that's just the gauge would malfunction for a minute. I don't think that's the wall of water, but because nothing else shows up in, like there's another couple of those alert gauges upstream, and they don't show that same spike, which would have come out of 4 Mile Canyon. So I think that might have been somebody pushing the panic button, maybe. I don't know, because I sure could have. Yeah. Well, it could have. I mean, that's one of the reasons. That picture I showed of the pedestrian bridge at Evan Fine Park, there's a lot of trees along Boulder Creek, and if 3 or 4 of those started to go in and then got jammed up against the bridge, that would have been, then things would have been a lot different. But that didn't happen. So trees are a real problem in floods.
Have you looked at any records from groundwater, like well logs and things? Because it seemed like in our area there was a time release effect where the groundwater table rose quite a bit and started flooding people's basements well past when a lot of the water had stopped falling.
That's a good, yeah, I mean, that's a really good point. And the short answer is no, I haven't looked at that. But if you lived in certain neighborhoods in Boulder, you could see that, you know, the little trickles down the street were going for weeks and weeks. There's still one kind of near our house. So, yeah, even bedrock, water coming out of bedrock was really sustained. And I'd be curious to see, like, what happened with water wells, like, out on the South Platte River, which penetrate a couple hundred feet into the aquifer. It's good, I think, to probably recharge a lot of the water supply. But locally here, I think it is evident from some of the sustained stream flow. I got an email from a lady who said, when is this going to stop so my basement will dry out? Thinking like, not for a while.
We have these flow measurements going back to the early 1900s, and you said in one case back to like 1880 or so, and that's what you're basing your probability studies on. But how many of those streams were actually regulated during like the bulk of that time period, or had mitigation techniques put in place? So in other words, what you're actually looking at is a regulated, mitigated stream flow instead of looking at real natural maximums.
So that's a good question, and there's almost no stream in I don't think there is any stream in the Front Range that doesn't have some diversion and or storage somewhere along the line. Diversion for irrigation is all over the place. We saw the map of ditches in Boulder County. It's pretty incredible. So sometimes you can see that in these peak flow records, that the peaks decline over time. And that's probably not a climatic signal, but what you're talking about, a human intervention signal. So that's one thing we look for. And in those records I was showing you, maybe I'm using two samples there. The long records that were 50, 60 years long or so. I didn't see those trends there. So there's ways we can look at those data to see whether the human influences, and I prefer to exclude those if I can, because it's certainly been a big deal on some other rivers. Colorado River, for example, has been affected by lots of reservoirs. So you can see that very clearly, the flow is declining over time. So here, urbanization, likewise. I mean, the population in Colorado has spread enormously just in the last 20 years. So that provides more impervious areas. That would probably cause peaks to go up. So that could be a factor too. Good question, yeah.
So is the Boulder flood control seemed to work pretty well, but are there places where there were problems, or are things that are going to change? Because I heard about some culverts that got totally blocked and going through yards and stuff.
Well, I think the thing that caught people by surprise is a lot of alleys and just little side streets became these torrents, you know. And so even though the flow in the creek was pretty well contained, if you will, there was kind of mayhem going on just in residential areas, specifically up by University Hill, you know. There's a little Goose Creek, is that it, that comes out of there? Went nuts. And so all these streets and east-west flowing streets kind of became torrents, and I don't think anybody was kind of planning for that. Now, what will they do? I don't know. I know that I live in Newlands neighborhood, which is in North Boulder, and they just recently reevaluated the 100-year flood of this little creek there, and the residents were pretty upset about this because now all of a sudden their insurance rates were going to go up. Well, they have an empirical test now to know whether this was a valid designation or not. So it'll be interesting to see what comes out of this in the long run in terms of changes. So, I mean, they just finished all these floodplain maps and stuff, you know, and now to redo it. So I don't know. I don't know what they'll do.
Do they know why the water was pathways, and also also, like, Table Mesa was full of, like, boulders and cobbles and all kinds of stuff.
Yeah,
I'm not sure if people were expecting that.
right. And that, would that be Bear Creek that did that? And so, you know, again, they might have had culverts and things sized correctly, but trash got in them, or, you know, debris. Could be anything, and then, you know, then it's just, creeks are free to go wherever they want.
John, you showed there was one graph where I think it was Boulder Creek, where the stream flow really didn't start to have much in it until maybe on the 12th, and then, you know, then it started to jump up on the 13th. And the 13th was a Friday, but the rain actually started on Monday.
Yeah.
And it was really dry that weekend. I know because I was coming back from the Medicine Bow area with my son, and it was just really hot and dry. And we just figured, well, you know, it's the way the fall is going to be. And I'm wondering if, and the rain it was kind of a gentle rain. There was rain on Monday, rain on Tuesday, and it was kind of a gentle rain. And if it rained really heavy, like it was doing on Wednesday night and Thursday, with it being that dry, I don't think the ground would have absorbed it. So did it help that we had this gentle rain that kind of started to like break up the dryness and allowed like the, I don't know, porosity or absorbability or whatever of the soil to sort of absorb some of this moisture?
Well, I think that's a good question. I don't think it takes a lot to saturate the soil in Boulder County in general, especially in the foothills, because the soils are very thin. It's mostly a bedrock landscape. So that earlier period of gentle rain perhaps did build up soil moisture a lot, so that anything that fell after that, basically, it was rain falling on a parking lot, essentially. It was already saturated soil. So maybe that monsoon flow, the WCB, was responsible for what you're talking about, and then the other upslope flow was what brought the real higher intensity rainfall on Wednesday and Thursday. Oh, I see. I've been asked questions like this before. The idea that really dry conditions limit infiltration, is that kind of what you're asking? And I don't think that's the case. That the drier soils are, generally the faster they suck up water, to a point when they become saturated. So I was thinking maybe you were asking, did the preceding rain, was it enough to saturate the ground? So soils, when they're dry, they actually act like a sponge. They draw water in under tension. But anyway. Okay. Well, thank you very much.